Oh, then we can go back to whining about time. Oh, here's Aaron now. Yeah, hi, it's Coffee Compiler Club. Everything to do with, compilers and language runtimes and garbage collections and time zones are all fair game. Whining about parsing time. Should have started recording earlier. It was a good yak about getting time zones correct. You're being recorded. You'll show up on YouTube within an hour. If you don't like that, bail out. I don't have a set agenda. I will start by saying several people missed the opening hour of the SSA talk. Does anyone want to have any questions about SSA as an opener?
Why did you choose? Why did you choose an SSA representation for your AST for your?
Not for my AST.
It's not AST. Okay, it's for your IR. Yeah, correct.
Why did I choose SSA?
Mm-hmm.
Well, you wrote a college paper about it.
That was my thesis. So, SSA was hot and exciting in the late 80s. I was, bleeding edge. And the integration of SSA and the people rewrite rule game got me a compiler that was running in provably linear time in one pass and incremental, so you could always stop at any point and have a correct IR that had been, partially optimized. And holy shit, it was way the hell faster than the things that were around at the time, which were always running pass after pass after pass. You ran a pass to get rid of some dead code. You ran a pass, you folded some contents. Well, that made some dead codes. You had to run the dead code pass again. And, lather, rinse, repeat. Most compilers ran 20, 40, 60 passes, and I'm not lying. That, that was a kind of a standard count. And they were slow. And I was doing everything that all of those passes did all at once in, provably linear time in one pass.
Hire 4 people to write you a compiler, get a 4-pass compiler.
Yeah, well, as a minimum.
Yeah, more specifically,
needs like 4 passes just to inhale code and to, breathe, and then they need 14 more to do any kind of optimization. So I don't know.
Yeah, but you choose to output SSA directly from the parser, not on
okay,
on
so
IR.
That's AA. So, in the land of Java bytecodes, I did bytecode to SSA because I could, because it was easy, because it was essentially doing DAG, just extended the DAG to the multi-basic block paradigm. If I had, back in college days, everyone did an AST, and then you did an AST to whatever your IR was. And that's what I was doing too. Honestly, we went to a tuple-based IR using somebody else's tool, so I didn't have to parse C code, right? And I had a basic blocks and tuples that I then turned into SSA and then went to CF nodes and that. Fine. Go to bytecodes and at Sun, and I was like, well, this is just like the stupid IR I did at Rice. I'll just go straight from bytecode to SSA. Easy, cheesy peasy. Didn't have to think about an AST. By the time I got to doing AA, I was like, fuck, I can go straight to SSA from anybody's format, including C or AA, and I can do type checking on it in the same linear pass time. So I'll just skip the middleman and go straight to the one IR.
Wouldn't it complicate things, because you need typically one for the front end of the AST and then generate an SSA for a more heavy stuff for like optimizations?
Well, that's what I'm saying. I skipped having an AST, so I don't have to build an AST or have an AST data structure or think about AST bits at all. I'm going straight to, straight to SSA.
Well, your SSA is your AST.
Yeah,
it's not a tree, but it's having the same, right? No, but it's important because it's doing semantically what you would otherwise do with an AST. It's doing your type checking, but it's not a tree. So I get to do other things with type checking that are not necessarily tree-like.
Yeah, that was my question. Do we lose some semantic stuff?
I'll bet you are forced to do, well, I know you are, you do a flow pass over the AST, which is fine, but I'm getting the flow pass using my same fast linear time algorithm out of the graph format, and I don't have to change IR representations again.
Right, but basically, the difference between your SSA, at least an early stage, versus versus an AST, is that the AST, so to speak, dangles from the root. And in your case, you actually pull the threads. So say you have a loop. So you've got the two phis, one for the leading edge of the loop and one for the second to end pass of the loop, right? So all you do is you pull that string. So basically you take the loop twice, but it's still the same, other than the,
You only get it once. You only get one phi per variable that's running around the loop.
well, so no, you have X coming into the loop, and then you
Yep.
have X on the second to end pass of the loop.
The,
And the X on the X on the
back
second,
notch.
end- sorry, the X on the second pass points to the X on the first pass.
You only get
That's
one
not-
phi, and he points to the two different exits. Yes.
Okay, right. Yeah, I was actually thinking of it this week after your talk last week. I was thinking of it almost like a knot where you pull on the string and the knot disappears.
Yeah. That's how I think of it.
Because we have a different, so I didn't have to deal, it's a long story as to why, but in our case, we actually have to, we have a conditional second go at the loop. And that if a loop is nested, that means you could have up to 4 goes, 8 goes, and so on, right?
Yep.
And I
That's
was
a well-known algorithm issue with using AST-like things to do loop things. If there is an ordering on the loops and you do them inside out, you can usually get away with the one pass. And if you don't have an
Right.
ordering that makes sense, you can accidentally require some larger count of passes. I don't remember, it's n squared or something. You can get more passes required to come to closure on most flow algorithms. So if you're doing a flow algorithm basically to verify typing and you don't do it inside out, you can be stuck.
Right, because we use it for type inference. And remember that we auto narrow and auto widen based on what happens.
Right.
So at the start of a loop, the first time, the value might be known. So it might be a declare type of string or null, but you hit the loop and everything you know up to that point says it's only a string. Someone sets it to null in the loop. So your first pass through, you think, oh, this is definitely a string, but then you have to repeat it because you know by the time you get to the end of the loop that it could have been string or null.
Yeah.
So you have to say, no, I have to change my assumptions and replay that pass.
Yeah. So the general issue there is you're doing what you just described is doing an optimistic pass. I'll assume no null comes around the back edge, but you need to find closure. You found the null, you have to go again. Those things can go in squared on deeply nested or irregular control flow, which maybe you don't need go to, so you don't have any bad control flow. And the linear time version of them, there is a linear time version of them that basically does SSA. Starts with SSA, and then you can yeah, you can go linear from people who do it on ASTs usually play some game up front on the ASTs to get the good ordering, and then they're limited by the count of times the value can change, which is just the same thing I'm limited on. When I do it in the lattice format, I'll say your high value, you're a string, you're a string or null, and it's falling until it stabilizes. But I only have to do it in the count of falls times the times size of the program. It's the max. Count of falls is usually 2. So what you described is reasonable, except that you can hit, because of the loop nesting, you can be required to rerun whole loops on things that you could have discovered in the first go round. And that's what the SSA gets you. So I can make a counterexample. I can go hunt up counterexamples. I don't want off the top of my head. Fine. For well-structured control flow, you should be able to find your loops inside out.
Yeah, I was playing with it in my head, and I think SSA would turn an n squared into a 2n. And I think that's a good example of why SSA at that level would be. And I never ran into this before type inference, right? So in Java, where you have no type inference, like 2 passes and you're done, right?
Because you're not doing the optimizer.
No, not even the yeah, exactly. So I mean, I'm not talking optimization. I'm talking source code to byte code.
Yeah.
It's 2 passes in Java.
Yeah.
When you have type inference, though, particularly as you're changing as you're changing your dictionary or whatever you want to call it, your context as you go, type wise. That's where these types of things come in. And also the other one that we ran into that caused potential replays was a capture. So nested capture implications, because we have 3 different types of capture, and it's all transparent. So we capture value, or we capture immutable reference, or we capture immutable reference. So
yeah. Same
I
kind of
think
a lattice fault count issue, get to repeat.
I think captures are easier in AST instead of SSA, or no?
Nah, makes no well, it makes no difference to me. I capture too. I mean, I have nested closures where you can have exposed, upwards exposed fun arts and shit like that. And it makes no difference.
What I decided was, because I've only started but haven't gotten very far in it. When I do the bootstrapped compiler, I'll do it in SSA instead of from AST, or a very early transition from AST to SSA.
Yeah.
So the modern approach is SSA instead of AST, directly from the source.
That's me.
That's Cliff.
Yeah.
I'm thinking of doing it mainly to learn it and to see because I'll have then side by side the same language, 2 different compilers to compare.
Right.
I'm
I
starting to.
I did that side by side hack when I was in my mid-20s. Right.
Okay.
I'm in my mid-20s now, so.
I started to grok the SSA with a quick glance or from the last presentation, but I'm pretty far behind regarding the SSA representation or even CF nodes. But I do believe that it can pay off to generate SSA directly.
Is this going to be helpful here? Throw up the slides. Do you have a specific question, or are you still noodling it around?
I get the impression, the big idea, and how it enables an optimization, but how should I say it? The count of optimizations you are talking about, I'm still trying to figure out how to do them linearly, how they would work in side by side instead of one pass over the other.
Okay, so that's not that's SSA and algorithms. It's not IR per se, but the algorithms kind of come in like 3 flavors here. There's people rules, there's optimistic flow, and there's pessimistic flow. Pessimistic flow is the bottom up. I'm discovering new facts because I found that X was a constant too. So the multiply says I have 2 constant inputs. I do constant times constant. I get a 4. I can be replaced with 4. So the flow version of that says I computed a 4. The people version that says because I computed a 4, I can be replaced with a 4 computation and get rid of the multiply, get rid of X. The optimistic version is a flow analysis only, but that's the one that Cameron was just starting about, where I don't know at the head of a loop what I might discover on the back edge. I'm going to run forward in my loop here. I don't know what I'm going to discover on the back edge for some, for instance. So I'll start with some optimistic value and then discover that it's wrong, and I have to move it lower in the lattice. In Cameron's case, he said string, and then he said string and null. That would be lowering in the lattice because you added an or null.
Right.
In case,
so you have a compile time. You have a compile time type. Say it's a string or a null or string X, and you say null or string X equals hello. So you know it's a string, right? And now you hit your while loop, and it's like, I know X is a string, right? So you're not going to use that knowledge for assignment, of X, but you'll use it for any analysis of X. So the first line inside the while loop says, if X is null, and the compiler is like, you idiot, X is never null here, never, right? I got to this point and X is not null, right? And a couple lines down in the while loop, it says X equals null, right? Or, if something, then X equals null, right? So In other words, the first pass through the while loop, the compiler is certain that X is never null. But when it gets to the end of the while loop and realizes it's repeating, it's like, I'm certain X could be null, right? So how do you feed that information back into the leading edge of the loop so that the compiler doesn't realize that X is never null, right?
So this is the difference between an optimistic pass and a pessimistic pass. The optimistic pass makes optimistic assumptions that aren't necessarily true. You have to reach that fixed point where you have all the same answers for everybody, and we all agree what those answers are, before you can transform the program based on that knowledge. Whereas with the pessimistic approach, as soon as you discover a fact, you can immediately transform it because it's correct on the spot. But there are certain facts you cannot discover with the pessimistic approach that you can with the optimistic. So the easy way to, so I can do that. Let me get rid of the share here and go to a chat or the doc here. Go find the doc.
I don't think this is all specific to the representation. I think you can have both approaches like in non-SSA representation.
Yeah.
I don't know why would you do that, but you can.
Yeah, this is not specific to SSA here. So let me see if I can come up with a example in the docs, and I'm going to screw around and fail to get it correct several goes around. Well, let's see here. So, you know, what's the value for X here if I'm doing this in a, what I'm going to call a pessimistic approach. So a pessimistic approach says, while I am just looking locally, can I discover a fact? Well, I start with X is 1. I hit a while loop. I don't know what X is around the back edge. So in SSA form, I'm going to relabel these things to underscores. So, you know, what's the value at the phi? Well, I don't know what X2 is, so I have to assume it's horrifically mangled, and so I don't know what X1 is. So I'll claim it has to be constant. I mean, it has to be an integer, but not a 1. Then I do 2 minus some integer. Well, that's any old integer, and so in fact, I hit a fixed point because X0 is 1, but X1 and X2 will be some integer, and I'm done with my pessimistic analysis. There's no more profit to be had. If I do an optimistic version, I'll start with, you know, X0 is 1. I hit the top of the loop. I have something around the back edge for X2. I'm going to assume it's every possible integer constant on the planet, which we would call top in a lattice, or I call top in a lattice. Different people call it whatever. It's the most optimistic value. Okay, so mixing that with a 1 says I could be a 1 here. So I replace X of 1 with a 1. I do my math, 2 minus 1, that's a constant 1. X2 is now a 1. I bring it back around. I have 2 1s at the head of the loop. X is a 1. I found the constant 1. So optimistically, I find an answer that pessimistically I never can.
So we can say that optimistically flows from more general to more specific, and the optimistic approach came the other way, from more specific to a more general approach.
Yes. And the optimistic approach has to hit a fixed point before you know for a fact. So there's another version of this test which uses exactly the string problem here. Well, I'm going to add conditional control flow to make it, but it's the same algorithm plus conditional. Oops, let me get my phi in here. That'll help. Let's see here. X sub whatever 3 is going to be equal to. I'm probably not doing this a good example here. I want to do it this way. If I want to have another null, I need to throw in here. Is probably what happens here. If this is a null, then set it to a null, and you know we can claim this is a stupid thing. But basically, it comes through and I say, hello, is a string, and it's not a null. And X2 at the head of the loop, I compute X1 from X0 and the back edge, which I don't know yet because I haven't seen it because I haven't parsed or my algorithm hasn't run, I'll assume it could be string or null. So x1 could be string or null. Well, if it's a null, I'll set it to a null, which is kind of useless. And then I'll mix in a null with whatever I had before, which was string or null. And now when I come back to the start of the loop, it's string or null. And I don't know anything about the nullness of x as a variable, or x1. Whereas if I do the optimistic version, I'll say, hey, we'll assume it's the better of string or null around the back edge. It's whatever it happens to be. It's the string hello around the back edge. So I'll bring in x1 as the string hello. I'll say that's not null. So I won't execute the 3 part, the x of 3 part. I'll go to x2 is now only getting from x1, which I'm assuming is hello, which I bring on the back edge, and oh, look, it's hello, and I'm done. And I discovered x is hello. It's not modified in the loop. So this kind of null check optimization games are actually really common in Java because there's a bajillion null checks running around. And people do stupid shit on the null check sides where the nulls can't happen, and you actually get a real profit here. Whereas in C code, people don't write things quite so stupid. But you get stuff after inlining, and people have constant flags on how they gate library calls and shit. You get stupid shit happens. Anyhow, the optimistic version here says I find something where the pessimistic does not, and I can prove that's monotonically better than the pessimistic version. That is, there may be nothing to be found for either, but there is always, not always, there can be things that the optimistic version will find, the pessimistic will not, but the optimistic will always find everything the pessimistic will find. That's the right way to say that.
Okay. Okay, because it all works because it's monotonic framework.
And it all works because it's monotonic framework. Yeah.
Okay.
Should have done this a little while ago, and then other people, viewer, can watch it later.
Yeah, the pessimistic version always what it finds. It's always correct. You can rely on it. But,
Yep.
But the optimistic kind of starts from more general assumption and tighten that up in the course of the monotonicity.
Yeah. Yes, because it's correct at the locally you can, and then because it's correct, you can now optimize with it immediately.
Yeah. Okay.
So the deal with the SSA here and the people rules are basically a more aggressive version of the constant folding I'm doing here, where I can do many other things besides the sort of classic constant folding games. Let me find a stupid example here. These are probably less helpful. So in the land of doing constant folding around primitives, all my primitives have a 1-line declaration in Java that basically says I'm a primitive, I have so many arguments in and out, and they're this type, and they have one operation field, which I'll throw down what some of this looks like here. So here's code from primnode AA. The font needs to be shrinked to put it on one line. Let me shrink the font here. However, I find font shrinkage. Where do you find?
It's look for the 11.
I found it. Yeah. Thank you. Okay, come back here. Okay, so it's entirely readable in my monitor. I just threw it in one line. So and there's just way too much Java ceremony here, right? If I get rid of the public static class extends public Boolean words doubles, the line would be like, so there's a lot of Java ceremony here. But you can see I just have some stupid op on the right that just does some stupid thing. So there's a wrapper around this that says, look in the local area around my node, see if I have these constant values. If so, fold it. It works for all the primitives. So all the primitives have, let me go find the wrapper code. It's really stupid enough here. It's all very boring. Well, this is all. Let me go. There's the are you an error case or not? Yeah, here we go. Oh, this is all like a one-liner here. Those are the two op. Let me go find the prim to rel op. Yeah, right. Okay, whatever, fine. Yeah, you got color choice grew you, and then you can't, it doesn't land in one line. So you can argue here. Whoops. Okay, so I'm gonna get rid of override and shrink it here. And let me get this down to here. So basically it looks like on the rel2 floating point ops, there's this apply line that says, go to arg0 and get the double, which I'm here because I already know I have constants because I didn't show the next layer out wrapper had checked for all constants or not. Get the arg1 constant and compute the op, and that gives me a true or false as an integer type internal to the IR. And so I have, you know, all my rel ops do this, but all my double float ops have the same one line for returning a double value that you computed from op and so on and so forth. So in, you know, 20 to 30 lines, I have all the primitives doing people optimizations where they constant fold on themselves. And then I have a similar set of lines that are similarly sized for doing ifs that are dead and control flow diamonds that do nothing, it merge nothing useful, and fees that are dead and dead control flow paths and fees that merge the same thing and whatever. You go on and on and on. They're all turn into, depending on how fluffy you like to write your code, they turn into, you know, 3 to 5 lines, 10 lines if you like a lot of white space, but all doing something conceptually very tiny. I look at a little region of the graph. I see that there's meaning, program meaning that I can reduce to some way that it's obvious, and it's almost always something completely trivial like this. Like the fees with identical inputs, that's totally the same kind of logic here. And that's just meant that I inserted a junk fee during my SSA conversion that after some optimization was discovered to be junk. And so I'll get rid of it. Let me see if that one's readable without I chart on you. Deal reduce, it has a bunch of dead shit. Here's the core loop, which is a little more complicated than you want because it does several things at once. I'll throw out the core loop here as being a little more complicated than it ought to be for this kind of a scenario. But basically, oh, and it lost all my indentation. I believe me, I actually like my code indented. Let's see here. We could argue my indentation. So it says I have a fee. I'm in the middle of the fee node people rule. So the people rule is doing a look at myself, look at my inputs. That's def's length. This is for all my inputs. Grab the region. Well, it's R. That's my control that says I'm dead. So this is the one that says dead path. So ignore dead path. Otherwise, I get the thing that is the input for input number 1. And I might have an in-way merge, but if I only have a 2-way merge, I'll be doing, you know, 1, 2, right? If I find myself, then I merged myself as a self loop. I didn't do anything useful. If I find the one other thing, which was the live as null thing, then I again found only one thing. And so I ignore it. If I find that I don't, if I find something else, but I haven't found a one thing, then I go ahead and capture it, the one unique input. And otherwise, I give up. That's the, I'm going to give up now. And then when I come off the bottom here, if I found one live input, then I replace the fee with the one live input. So this is a middle of a graph rewrite rule that has said, I'm a fee node. I have some parameter. I'm only looking at my one adjacent neighbor parameters. That's my input 1 or input number 2. It didn't go far into the graph. I look, are all my inputs either myself or one other unique node? So there's only one unique node I'm looking at. If that's the case, I return the unique node I'm looking at, and the surrounding context does the rewrite rule, which replaces, I'm not showing it, just replaces the thing by hacking the graph edges, throwing the fee away. And this is a sample rule that does something a little more complicated. It includes in there the X control line is saying, oh, I've proven this input path is dead, so I'm not going to count it. Even if it has a value, it can never execute. So I'll just ignore it. And that's a pessimistic X control rule. It doesn't work I don't do this during the optimistic passes because everyone starts dead in the optimistic passes. And so everyone would be considered a dead path and be ignored. That's not correct. But in the pessimistic path, I discover an input edge that's dead. Then at the merge point, I will not merge it.
So do we switch from the pessimistic to optimistic during traversal, or how?
I treat them differently. So I will do pessimistic while parsing because I don't know yet what the unparsed program does. And as part of the conversion process, those maps I've showed on the slides, they all keep alive, if you will, the unparsed program. They represent all possible future uses the parser might yet discover.
No, yeah.
Okay, so mostly I can't do a lot of things anyhow because I have uses that are unknown what the hell they're going to do. And the fees all have a back edge that comes in that I don't know what it's going to say. So I can't do any of these kind of games on that. But after the parsing's done, a lot of those issues start to go away, and I start to clean up as I go with the pessimistic rules until that stabilizes, just because it's cheap and fast and gives me an obviously easier read program. A lot of the junk fees go away. A lot of the junk computations go away. I can look at the dumped IR and discover that it matches my intuition of what the code I just wrote is supposed to be doing. Okay, fine. Now I have to run an optimistic pass to do typing. And so the optimistic pass is a separate standalone thing that says, I'm doing the optimistic pass. And at the end, I come up with new types for every node, new Hindley-Milner type variables, polymorphic type variables for every point in the program. That information is now fed into the next pessimistic pass as the starting point for things. And that pass suddenly says, oh, I have all these new constants I didn't have before. Let me do them. A lot of the constants are dead control, constant control, which will be dead control, X control there would be the dead control. And I'll go kill off dead control paths and things that don't make sense get whacked away. And then when that's done, I'll have the well-typed program. Like the pessimistic version may have places where I say, here you are mixing strings and structs, that's illegal, but I will survive, but I won't do any optimizations because I don't understand what it means to have a string and a struct mixed in the same variable. This is not supposed to happen.
So we start with the pessimistic approach where there is information not yet known, and when we know more about our program, we start with our optimistic approach, which is more aggressive in optimization because it can assume more things.
Yes. Yeah. In AA, there's one other hit there, which is I have to do typing with the optimistic approach, or I won't get the correct typing. And you heard Cameron just say strings and stringer null. That was him doing an optimistic typing as well on an AST, and I'm doing it on a graph, but it's an optimistic typing. And as I guess Arthur was just saying, this is not related to graph or ASTs. This is.
So what makes them work kind of back to back together, the multiple optimizations, is that they are monotonic. So they cannot get it wrong, maybe.
The reason that you can do pessimistic hacks back to back to back is because they're all locally correct. They're all monotonically correct. And they in some way reduce the program so you run downhill because the program gets ever smaller, right?
Oh, yeah.
Until.
So it turns out that if you have your monotonic approach, it turns out that is useful. Yeah, who knows?
Yeah, who knows, right? So the people rules are monotonic in not just in the lattice, they're monotonic in the graph. In this case, the one you're looking at here for phi, when he's done, he removes a node, strictly removes a node. So this optimization, if you will, is one that strictly reduces the graph size. And I have a set of them that strictly reduce the graph size. I have a set of them that will not reduce the graph, but they will not increase it, but they will canonicalize in hopes that I will get future reductions. And then there's a handful of ones that grow the graph node count, but reduce some other property. And if I don't have that monotonic, some other property got reduced, I can be in an endless people rule loop where I endlessly unroll a loop or endlessly do something stupid over and over again, like flopping back and forth. Like I want, all my constants to the left of an add, but I have add of two constants. And so I flop them left and right constantly. So something stupid happens and you get stuck in infinite loops. And Hotspot, we went through a lot of those issues and teething them back at Sun. Well, we sorted that out. It's not too hard to come up with what it is I'm reducing. That's a program-wide behavior. As long as I have that, then I know I won't endlessly cycle. In fact, it'll run downhill.
Turning back, that's why you wanted this monotonicity at all costs, because it makes all of this hold them together.
Yeah. The monotonicity means I hit a fixed point, and there is a fixed point to be hit.
Yeah. So if there is some kind of clash of features that do not go well with monotonicity, we won't have that feature. We'll sacrifice.
Right, like the classical compiler things that I used to do way back in the day, all had the property that they ran a bunch of passes and then they were done, even if there was more to be had, because they weren't certain they weren't going to be churning left and right and left and right and left and right. So they did a pass and they did a pass, they did a pass, and then they, incrementally the gain for doing another pass got lower and lower and lower, but they did a few more passes and then they sort of dwindled off into the weeds, but then they stopped. And if they instead had a loop that said repeat until nothing more can be happened, these 5 passes, they would get stuck in cycles where they would endlessly churn. So there was always a breakout that said repeat until there's no more progress, or I did it 10 times in a row and then give up.
Right. So monotonicity guarantees you that it's computable. Why do these things tend to be linear?
It's not 10, it's hard forced linear. Okay, and that's because, so there's 2 different theoretical proof notions. They're totally related by the monotonicity concept, but there are 2 different ones here. In the land of value computation, for the optimistic and the pessimistic doing value computation, the rule is I have a bounded lattice. The lattice has a fixed depth. Sometimes you call it a ranked lattice if you've open-ended on one end but not the other, whatever. Fine. You have a lattice of fixed depth, which means that somebody falls monotonically to chunk. They took one of the chunks in that lattice. Then they might fall again and again, but then they're done. So if that lattice depth is, say, 3, the worst that can happen is a node drops value 3 times. So take all the nodes in the program, the size of the program, times 3, the depth of the lattice. That's your hard bound on the number of times any value will change. Anything will change value. So if it's, I don't know if it's string or not, it's string and null as a bottom one, it's string, not a null, it's null, not a string. I have a depth 3 lattice. I don't know nothing, it's a string, it's a null, it's a string or null. Okay, that's a depth 3 lattice. I actually only fall twice. So in 2 passes, you're done.
Yeah, the limit on the number of iterations to fixed point, it has very practical reason to have it. It's just in case you have a bug and you have an infinite loop and it doesn't have a fixed point, well, you will terminate instead of like running in an infinite loop consuming resources if you're running in a VM.
So, right, so Hotspot went through a bunch of these rounds where we had infinite loops until we got it sorted out. And we had to have other cutouts that basically said the compilation failed. We tried a long time, the compiler's still going. You couldn't kill the compiler because he was holding on to VM internal resources that he didn't release if you shot him down because he was a C thread and he didn't do polite things when you shot him down. So instead you threw an assert saying, we have a compiler bug.
Yeah, we have limits for fixed point iterations just in case. It's not that we hit them. You like consider this an assert. Like in debug build, it is an assert. In product build, well, run, I don't know, 100 times and then give up.
Okay, yeah. Yeah, we ended up with a couple of places where that was going on too. And the compiler would be able to bail out at some point gracefully and say, I failed to compile. It's basically an assert. So
what does give up mean? Fall to the interpreter?
No, just limit the number of iterations. Fixed, like you didn't reach the fixed point, but you did 100 iterations. Well, continue with what you arrived to, and don't try to like get the.
You're still going to generate code from that.
Yeah, you hang on. If you're failing in an optimistic pass.
If it is optimistic analysis, yeah, we give up the analysis and recompute it pessimistically.
Fine. Yeah. Yes. Right. And I'm always doing the pessimistic one anyhow, so I just gave up the optimistic version, and then you carried through. Yeah, but sometimes you had bugs in the register allocator and it spun forever and you actually didn't get an allocation and shit. So there were times when you just failed to generate code.
So I have a question about, I guess it's about representation analysis. So how do you deal with flow sensitive type improvements which come from dominating type checks?
I do a cast, which is a join, not a meet in the lattice, and that's a lot of subtle, short, quick, subtle words with deep meaning. So now we can talk more about that.
So, I guess what I'm curious about is when you're doing your peephole rewrite,
yeah,
do you do the DOM tree traversal looking for like conditions which holds true at this context? Or you just use some cached result which you computed previously during optimistic pass? Okay,
so I think that was a false dichotomy here, or I know what I do, but I don't know that it matches exactly what you just said. So in the pessimistic side of things, there were several improvements done for dominating checks. This is not related to your type improvement question after I do an if test and I want to hoist somebody to say I passed an if, so I know something, like it's not null. So unrelated to that, if I'm looking for dominating checks, the C2 compiler keeps an incremental dominator tree in the pessimistic land. And he pessimistically incrementally updates it, which cannot be perfectly correct. And periodically he has to rebuild the incremental dominator tree because it got so dirty that it wasn't helpful anymore. And I just tied that up with whenever I flipped the IR between arenas during whole IR rewrites anyhow. An incremental dominator tree means that in very short linear time, I can, or sublinear, whatever, not quite constant time, I can discover if there's a repeated check, an if test that's been repeated anywhere that dominates, and then I can kill the dominated guy. So that's one thing. There is the optimistic versus pessimistic. In an optimistic pass, if he discovers new types that are stronger than what the pessimistic one, those are the types that the pessimistic one uses directly. They're not cached per se, they are the types. So there's a cache of one. It is the node has a field called value. My r.value field I highlighted in the doc share, that's a field reference for the ith input. It said in sub I, just like node in dot value field. That is the only one field where it has, that's your pessimistic value and pessimistic, and it's your optimistic value if you're optimistic.
Well, let's consider a simple example. You have an argument of type object.
Yeah.
Then you have a type check on this object, which checks that this is, I don't know, integer. And then you have a use under this type check.
Yeah, that's the third thing that I hadn't gotten to yet, which is you did a lifting test and you wanted to do something with the lifted value in the lifted test.
That will be discovered by the flow sensitive analysis.
I can do this in the pessimistic side by inserting a node in the graph that upcasts a value from object to capital I integer.
Mm-hmm.
Okay, so basically you introduce a new SSA value, and and that's what's sometimes called SSI, static single information, where when you have improved information about the value, you have a new name for this value.
I make a new name for the value that's only valid in the body of the if. The node is control dependent on the test so that it doesn't float too high and get used where it shouldn't. And it only gets used in the body of the if where it's been guarded. And there's a bunch of hacks around that as the IR, but it's a graph rewrite rules that are annoying to deal with, but they're there. They're just the standard.
Yeah, got it. That essentially was my question, because what we currently do is we have to, if we want to ask a type query at a particular context, we'll need to walk the DOM tree looking for conditions which hold true there. So we don't do the rewrite. So we'll look at the original SSA value, which is object in my example. Then we walk the DOM tree looking, is there anything which can improve it? Yeah. And it works, but it costs some compile time.
Yeah.
And one of the alternatives is to do this kind of rename into SSI form. But there are some, now you need to teach the rest of the optimizer that they use this extra rename. It needs to see through.
Right. So at the time that I parse, I have the parser observes the use of the value underneath a guarded region and the bytecode level at the C or AA semantic curly brace level. And I have limited count of uses of that value. They become a new value, a new node in the SSA graph, which is, like I said, it's my cast up node, does a join in the lattice instead of a meet. And it's control dependent on the text. Okay, then I'm done with that that's all I had to do there. If later the if test during his normal operation does a peephole check and sees a dominating if test, he will wipe himself out and go to the dominating test. That act will lift the dominating control on the upcast to the dominating place. If that same test had also a cast of the same value to be lifted, those two things now value number identically and fold into the one, and you now get that value uplifted over the entire region for no more cost that I'm already doing value numbering, I'm already doing dominating if test. I had to do nothing else than insert a cast in the graph at the local time when I first discovered at parsing that I had a thing there. And then now I have the lifted value throughout the broadest possible region it could be lifted.
So essentially, you get this update for free because you don't have it scheduled at a particular location. It's just guarded by a if condition.
Yeah, by conditions, which in my case, control of a test is a standard edge in the graph. So I'm just using graph edges for my dependencies. I get a graph edge on a conditional test, and it moved up to another conditional test as part of a rewrite where I just semantically replace one with another.
That's just another thing you get for free with this floating representation without a fixed schedule.
Yep.
Although the problem, okay, with fixed schedule, we would need to have a transform which lifts them up. It's fine. It's just writing some code. But what I didn't like about this scheme is that I would need to teach other places in the optimizer that there is this rename it now needs to know to look through. Like, for example, if I constant folded the original value, like in the example, it was an argument, but imagine it's some value which we constant fold. And then I need to know that, okay, I need to constant fold through this rename.
I got that for free as well. I can, show you. I was going to show an example of doing this thing, but I can pull up the rename, the code for the cast, which the computation on the cast here basically says you take your input and you do a meet in the lattice instead of a join. I mean, a join in the lattice instead of a meet. Sorry, and I'm done. So if you had a constant coming in, it got joined with the thing that says, "Oh, I'm no, I'm not null, I'm hello," and I'm as a string, as a constant string, and I joined with not null. Well, hello's not null, so it just got hello out, and the value on the cast was hello again. Right? It was nothing to it. Constants flow through these things directly, like anything else.
So okay, you have a pass, or like you have analysis which can forward information through these renames. Do you have to know how to look through these renames in other places? Let's say in some peephole rewrites.
There are a handful of places where it's useful to look through them. So it's not never, but it's only if I'm looking already far afield and I'm looking generally for some sort of equivalence relationship that's non-obvious. So it happens, but it's actually really rare that I need to do that to get anything useful. Like if places where I did an if and else and have a diamond and I have an uplifted type I did something cool with, and then later there's some more code in the middle and I have another diamond and I have the if and else and I want to use the prior guy's computation on the other prior diamond, instead of trying to say I found a dominating test and go find the uplifted value and see that it's both uplifted and see that I can do something, instead I do an unzipper thing where if I have an if test and I replicated if test above it and below it and something in the middle, I just replicate the shit in the middle and I do the test once and have, I know it here and I didn't here, and then I have the zipper duplicated and then I know it here again, and then now it's the same thing in straight line and straight line code. So I'm going to attempt to write some kind of reasonable example here where I'm going to do an uplift example if I can make it work well. And so basically, I introduce a cast not null value node in the graph. Which is full SSA we name here.
Cast not null is a narrowing cast. It doesn't make it a specific type. It just makes it the not nullable version of whatever it was before.
Yes. And everyone loves narrowing versus widening. Oh, come on, Google. How do I make you lowercase? Thank you. So in my case, the cast is completely generic and it's based on what the test was. Not null is the common one, but I could say x equals 5. And then in the arm of the thing, I would have a cast to x to being 5. And then it's a 5. And I would do 5 like math with it, right? So the unzipper test that I was talking with Arthur just a second ago is the version of this that says, here I've tested x for null twice with some shit in the middle. It would be nice to know that I had x was not null on both of those 2 arms. Oh, my comment above is like junk. So somebody's up there with the comment hack. Let me go get rid of that comment here. It's just like, yeah, there you go. So the zippered version of this is the one where I take the ... some other stuff here, and I replicate it and do the test only once instead of twice. And then I end up with 2 casts of not null of x. I actually should do that here. And they become value numbered equivalently. And then the x1 and x2 become the same thing. And it's the not null version of whatever x is. And x1 and x2 become the same thing. So x.field and field2 do obvious things that you would get out of the thing. So I don't know if people need to see that in action or not. It's a reading. And then Arthur's other question was, is there times when I have to peek through the cast to get at the original x sub 0? Yes. Is it common? No. If I got lost all of those peek through casts, would I lose a lot of optimization? Almost none. There are a handful of places where I discovered it was interesting and I did a little work on it. In the land of AA at the moment, I'm not doing it anywhere. I'm kind of a goal I'm having right now is to not peek through the cast because it does lead to funny issues. The funny issue you have here is that the cast secretly, which you can't write in C-like code, has a control edge on the if test. So up here, I'm going to extend someone's careful coloration and put an if test control point, which looks kind of like a label, but it's not really a label. So I'm going to call it here, label, and it's not a label. And this guy has an extra edge that's called label, basically. Now I have graph node for the label thing. It's not a label. So that's maybe doing you a disservice because it looks confusing. This is label 2, obviously, not obviously, fine. He's busy.
What's the label used for?
It's holding control flow. That's I shouldn't use label. So let me try, control. It's not a label.
Yeah, I think
does it here mean go to target essentially?
It's a source of the go to.
It's the source. Yes. So in the SSA, sorry, in the sea of nodes, control flow is represented like nodes in the graph, like anything else. There's no basic blocks per se. There's just more nodes.
So it's bidirectional. Is that why? Because you have the from and the to?
And there's not a bidirectional. The edges are all directed. So you need a graph picture for this. So let me. I'm trying to think if I have an older version where I showed this guy of the sea of nodes as a presentation. I don't have one right at too many talks. I can't go find one instantly. That's the issue. You need to see sea of nodes. My old paper here, IR95. I wonder if I can share this guy. This one is probably it. Let me see if this is a good one here to share. This is a really old one, and it's probably really the correct one. Control flow dependence. Here's a picture. Basic log. Yeah, okay. Let me see if this is really good.
So the things that you are casting here is the API of what names can interact with it, or is it actually the ABI of like the layout of the object?
Yeah, I don't have a modern. I have a really old picture. I can throw that up in here a second. So the difference here is that I'm showing a C-like representation. What it translates to is a node with these edges. A control edge called control 1 points to another node. It's an edge in a graph, points to another node. X0 points to another node. Okay, this is a constant. It's not a node. That represents what the cast is casting to. It's like a 5 or a not null or a string hello. It's some constant thing that I'm casting based on the test that I just did right here. I copied this constant here, I inverted it, and I threw it here. That's all I did there. Okay. So let me try. I have a bad graph variation. I have better ones floating around. I found quickly.
When you say invert, that's inverting on the type lattice?
No, negating in the constant sense. It's not. No. What I really did is I just lined up the control on the inverted of the test.
Yeah, I think the confusion here stems from the fact that the C-like code has kind of implicit schedule. You look at it and you think that things are sequential, while in the graph they are not. And you need to have this sequential relationship that this cast only holds true if you took the branch.
Yeah.
And that's what control is about.
Let me go throw up a different picture that's not very good, that maybe it's different enough to get people. Okay, so this is like a 30-year-old paper. So, you know, you have bad type formatting and everything else. So I have an if test. It has a true and a false coming out of it. And a region node, which is the head of a basic block effectively. So there is a control edge that pointed to the prior basic block effectively. So I can do a better, there's better diagrams floating around. I didn't have one handy because I wasn't doing SSA CF nodes presentation, fine. One of these control-like things, including the region or the true or the false side of the if there, is what is the node that is being talked to when I look at the cast. So imagine you have a divide by zero. You have a divide. It might be a divide by zero. You know you can't move it around because you get a divide by zero error. So it has some sort of control dependency. It says I'm pinned in place here. I can't go above some guarding test, because if I lift too high above a guarding test, I'll accidentally find the zero and execute too early with the zero and die. I have a load from memory. It has to have a null check somewhere, where I don't know where, but I can't lift it too high or I'll throw a null pointer exception and die. So all of these guys have some other dependency that says I can't lift. And the lifting guarding dependency for me is a control edge pointing to some piece of thing in the graph which represents control flow.
So each node has back pointers to where the control flow originates?
I'm using USTEF edges. Each node only has back pointers and not forward pointers, except I run them both directions. I talked about it last time I did SSA. I can pull that discussion out as well. The other direction is convenience only. It helps for speed. It helps for, but it doesn't have any semantic meaning. The semantic meaning is from the use, which would be the region I've highlighted, to the def, which in this case is the true arm of the if. So let me go here. Here's another region where select is really a fee, because that wasn't a common term back at the day. Here's a region that's ahead of a loop. The control comes out of it to the if. I have a loop back control, which goes back to the region. You get a bad arrow because I can't do arrows at, you know, Microsoft Word in the 1990s. So that's the, oops, somebody else shows up. That's the control region. So the outer loop where it says loop back control, the edge that I can't highlight with the mouse, that is a control edge representing cyclic behavior in a loop. There is some sort of add one and you know, do other things here where I'm coming around and pulling a data edge. So the output of the +1 goes to predicate. It goes around to the select on the fee. So I merged select, compose, and select and compose as, oops, I can't highlight them properly, as a fee. That's a fee. Those three nodes taken together are basically a fee. The only difference is I'm showing the fee is guarded by the region directly. And that's how I define fees from when I did this 30, 40 years ago to today. It's the same semantic behavior. So
Let me say, calling them select instead of fee probably would have saved generations of college students confusion.
Yeah, I didn't get that chance. That wasn't me.
Select is a much better term.
Yeah, fee, because IBM called them like fake, because they didn't know what to do with it. There's the hardest thing in computer science, right? Naming names. Select is better. So the edges are unlabeled, and up above I said an if had a true and a false labeled edge. I labeled them by putting a true and a false projection. If produces a tuple of two things out, there's a projection that slices the true or the false piece of the control out of them. So that just gets me back to the total unlabeled edges. Secretly, I'm labeling my edges with this projection hack, which means that I don't have to pay for edge labels if I don't need an edge label, which is 99% of the time, 90% of the time. So, however you want to define it as a speed hack or a layout hack or something, it's a convenience hack. I have bare unlabeled edges, which means they're bare pointers, which is part of the speed. And it's actually convenience for implementing and dealing and hacking the code. Bare edges are just a pointer. It's just semantically, it's obvious what the hell it means. It just points from one to the other. Then this false projection, I guess the true projection here would now correspond to, I'm going to whip the share over. If I can figure out how to stop the share and go back to the dock share, go back to the dock share. Where'd my guy hit screen share again on the dock share? Okay, back to the dock share. That true projection is what control 1 points to. It's a pointer to a node, which says, I am the true side of the if. The if has a predicate above him, which is x is unequal to null, or whatever the predicate is. So I have a graph. Let me see if I can find another paper here. It has a better view. Oh, here's IR95. Here's GVN. This is a better view. I should have pulled this guy out. Let me pull. Well, this is a guy without the. No, this is the version that I show on my easy SSA guy. It has basic blocks on purpose, but it has much better graph technology. It's written a few years later. Here we go. Okay, this is a better presentation here. Stop, this screen share. I believe this is this one. Yes, okay, so IR95. So nodes in a graph. Here is a region node with me showing a blue dotted control line to an add node. That's because I'm going to get rid of that because the add doesn't care to have based on some sort of control notion. Here I'm scrolling down. Here is a merge region, which is taking two basic blocks. So on the left, there's a classic control flow. On the right, there's the graph version of the same thing. So really, wherever you would have basic block 3, I have a region node, which I've called B3, but there's no name on it. Obviously, it's just a pointer to a region, just point to a node called a region node. And then there's a phi, which I like select. Yeah, it's a select. And the X1 and X2 and X3, you're selecting among them. Selecting X3 is either X1 or X2 according to whether B1 or B2 is executing coming in. And then the region merges two inputs. An if produces two control outputs, a true and a false. And in the next slide down, I'll show you the breakout, but there's regions behind it. So I'll go down. Now you have an if with a true projection and a false projection, and then there's the regions below, and that's controlling which region the if is true or false on. So this is me doing control flow. And
I'm sure these images will make perfect sense after I write one of these.
Yeah, and I'm sorry, I wasn't prepared to do a sea of nodes presentation today, so I didn't come in with like a lined up, ready to go modern version of it.
The next session.
Within the region and if nodes and projection, true, false, whatever, you can follow a subset of them, and that will totally give you a control flow graph. So there is a control flow graph buried in here, but it's not presented in the usual way. By presenting it as nodes and edges this way, I get to preserve, it's all just nodes and edges. Then my engineering doesn't have two layers to it. I don't have a control flow block engineering layer versus a regular data node engineering layer. It's all the same engineering. And this brings great ease in doing all kinds of standard node rewrite rules, people observations. Around control flow is just the same as around adding a 0. So I get a lot of convenience here in engineering the compiler by saying it's just another graph rewrite rule. It behaves just like all my other graph rewrite rules. I look at my neighbors, I pass a test on them, they pass the test, I rewrite them, usually many nodes to one node. So for instance, if this if test decides that his predicate, so I highlighted the predicate, is always true or never false or whatever, however you want to say it, it's always one side or always the other, then I'll say the if rewrites to the true projection, which is just a replacement rule, and the false projection rewrites to the X control constant, the dead control constant. Now a region, upon seeing the rewritten, I said projection true here, it's actually we rewrite to the top control. I'm sorry, you rewrite to the top control. The region down below doesn't know, doesn't care. He just says his input has changed from a true projection to the control leading into the if. And the second region on B2, his input changed from some projection of some if to the dead control, X control, as a constant value. Because he's a dead value, he knows he's dead. Or at least he might merge several values if you had some sort of horrible zigzaggy control flow here because you had go-tos or whatever. That arm of it is dead. He will delete all fees matching inputs on that arm. He will declare himself the X control dead constant. That's his rewrite rule. If I only have X control my inputs, I am an X control as well. I'm a dead control as well. And the dead control propagates forward as a graph rewrite rule, nomming up your dead program as it goes. In linear time, I've nommed up all the dead parts that were tied to the if test dying. Without an extra pass, it's all this workless thing running, turning along. So there is a presentation to be done here where I run p-poles to a fixed point on some obvious program, and you can watch it in action. It becomes very obvious. For me, it's been very obvious for a long time. For the guys who worked on the C2 compiler, you know, they had their you know, what you get now, their hazing ritual where they learned what the hell it did. And a month into it, they all had it, and they were like charging away full steam ahead.
Yeah, and returning back to the subject we discussed earlier, this encoding of flow-sensitive information via SSA renames is not specific to CF nodes. It can be done in any other representation. I
totally believe you. I mean, I haven't heard SSI directly, but it has nothing to do with graph. It has SSA, and as I said, I threw a control edge in on it, which I'm sure SSI has some equivalent thing, and then you're done.
Well, you can also do it for more analysis than the null pointer analysis. There's actually a nice chapter on this in the SSA book, which has a whole table of what are the analyses and what is your splitting strategy. Because it's essentially the splitting strategy that makes the analysis differ.
Yeah.
And you can also view this as you just cache the result of flow-sensitive analysis in your IR.
Yeah. Yeah.
And you can live without it. It's just convenient to have this information easily available.
For me, you know, caching in a compiler has always been the hardest part of getting the bugs out. So, you know, I have these stupid 3 things I say, you know, count by one is the hardest thing in computer science. Count by one, naming names, that's select versus phi, and invalidating caches. And exactly when you have to invalidate cache, like you have this guarding test that says the SSI information got lifted here, then you discover the if predicate is always false or always true. And you want to keep the guard, but allow the known improvement of knowledge to stick around. You have to do something, and that's a cache invalidation. And in my case, the cache invalidation happens because I just changed the guarding control edge independent of the SSI node. The cast node doesn't know, doesn't care. His control edge just moved. He didn't understand why, but now he's free to move to somewhere else in the program because the guard got lifted effectively.
Oh yeah, the more you encode in the IR, the more you need to rewrite when you do changes.
So there's less I rewrite when I do changes. I do a change and the SSI got lifted for me. I didn't have to do anything about it.
Well, I mean, if you you described an example where you need to do something to preserve this information.
If you had it labeled, yes. If you had it in the OIC as a direct, yes. If you had it directly in an IR node as I have the normal value, I have the lifted value after this if predicate, and then I change the predicate, I change the if, I have to be really careful with that cache value. The optimistic versus pessimistic guy does not, because of the whole monotonicity hack. He is the same value as the pessimistic guy, and it's the value that you give to a node. So an add node has a value like an integer. I'm some kind of an int, or I'm an int that ranges from 1 to 10. It's just the value. For control, the value is what I call control as a enum token in some fucking enum somewhere. It's a magic special thing. It just means I'm control or I'm X control. You're dead or you're not. You're one of 2 values.
Do you have in AA? Do you have control flow nodes?
Yeah, the IR. This is IR we're talking. The IR, independent of the language, for sea of nodes has control flow tokens, if you will, control flow nodes in the graph. So
Because in AA, I saw that you don't have control flow statements, right?
AA is using sea of nodes. There is definitely control flow encoded in the sea of nodes. There's not I don't know what you mean by statement. There's C-like statements that I write when I do the text form of AA. If I just replaced AA with the language C, I would write the same statement in many cases.
I'm just referring to, your while is like a variable, or if is a variable. I mean, I think I'm referring to that.
So as a separate hack, I'm exploring, can I have loops done in AA done via the Y Combinator and recursion, but give you a textual format that looks like you're writing a C loop.
Okay.
That was an experiment, and I may stick with it and I may not.
Okay. And do you have like a way to dump out the sea of nodes in AA, like in a nice format?
Yeah.
So that's a good way of understanding, right? So if somebody wanted to understand.
Right. So there's two levels of understanding here. When I'm debugging, I typically want to see a lot of detail on a small region of graph. When I'm explaining and exploring, or you're learning for the first time, you want to see a more holistic view, but I'm glossing over a lot of details because they like fucking details, and you're trying to get the holistic view. So when I do debugging, I typically have prints. I have a variety of prints that do nicely formatted graph walks and do dump a graph as a graph walk, reverse post order DAG walks, if you will, and print. And I print a node, it has a unique identifier. I give them a number, a dense integer number is a unique identifier. I give them a name like region name or an add or a load. I print out his inputs as numbers. I print out his outputs as numbers. Something like a cast has a constant like a not null, or I'm casting you to a 5 or a hello string or whatever. That's a constant shows up on that print. So it's just a one line for the one node, but printed out in order that is topologically correct within loops, modulo loops. Within loops, I play reverse post order or screwing around to get a little better printout. There's versions of this for C2 where I got much bigger graphs over a much longer period of time, where I also printed just the control flow slice. Only the reverse direction. Find all the uses, finds all the depth, print the depths. Print to a depth of 1, 2, 3, 4. Usually, 90% of my dumps are print to depth 2 or 3. Because beyond that, I get to stuff that's both correct and voluminous. It's the whole program, and I'm fixing some local bug. I've narrowed it down. Something bad happened when I did one people rule here. I'm after the people rule. The people rule screwed up. The graph is broken. Look at the graph. How is it broken? I need to dump 2 or 3 edges, 2 or 3 nodes worth, and I'm done. And so I do, and this happens all the time. So it's the shortest I can do. In Java, I say AA.p open paren 2 close paren. I get 2 left dump. And that's common everyday debugging hack.
I don't know if others would find it useful, but I think what I would find useful is if you could kind of give us a walkthrough of your code in AA for the sea of nodes, what the node looks like, what are the fields, what do they mean, and the inheritance hierarchy.
Right, I'm doing this in the IR95 paper on the screen right now to give a holistic view. To go into depth, I can, and it will go deep fast, and you get a lot of detail that's hard to piece together. Because I've done this for so long, I cut some corners on things. I'm happy to do that, and I'm just leery about how much it will help or hurt. So let me add one more holistic view picture here for an if on a loop, where I have start as an initial control. In AA, I have a start node. In C2, it's Sun, there's a start node. Sometimes it's called root, depending on your flavor of the day. He produces a control, which is the initial control for the region, which takes a control around the back edge, or goes around or falls in. The fall out of the region goes to the if, which has an exit control, which I'm highlighting with my mouse that you can't see. Has a true projection, which he loops back around. That's the control flow graph for this loop. There's a fee, might as well call it select. It has some initial value. It has some back edge value. There's an add one, which you bring around, I'm fucking incrementing in a loop. There's some tests I'm doing off the add one, which I guess I'll highlight here, which is producing some Boolean out condition codes. That's the old school name.
Am I correct that the projection nodes are workaround for lack of labels on edges? So
yeah, it's the other, you're correct, and it's the other way around. They are the best way to represent edges where I don't have to have a separate edge structure, because that was a nightmare when I did that.
Okay, so semantically, these projections are just labels on the edges.
Yes.
But as practical implementation, you have to have a separate nodes because you don't have a place to put a node.
That's correct. They're an edge label. So I can tell the true edge out of an if from the false edge out of an if. When I do a call and he returns, what the call returns, what does the call return? It returns control. I made it back. I didn't loop forever. He returns the state of memory. I hacked all of memory on you. Haha. I return some other value, whatever it is. Maybe if I'm Java, I return an exception, which the compiler represents as some of the thing that got returned from a call. I'm throwing in an exception. Here it is. So you got 3 or 4 things back from a call, which I grouped up in a tuple in the typing system as a collection of 4 things, and I use projection to slice out which of the 4 things. I didn't show here, but if I start a call, I'm at the function entry point. So not a call, but a function entry. There'll be parameters. And the parameters are basically pulling in all the arguments that got passed. And maybe you're not thinking of it that way, but it's the same as an edge label. Here's the start point for the function. Here's parameter 1, parameter 2, 3, 4, 5, 6. It's basically edge label.
Can we share a link to this?
Yeah.
This paper.
Yeah. Got shoved. Here it is.
And the end have some question. I move it down.
Okay.
The bottom of the talk.
Let me throw the link into the linky question. Links here. Okay, so it's called IR 95 by me. Printed in a simple graph-based intermediate representation, and it was printed in a workshop, IR 95 workshop. That's the name that you can hunt for.
And you don't have any of that code that you used for this lying around anywhere, do you?
I'm sorry, I don't have the code for what?
This behind this paper, right?
There's no code behind this paper.
I believe
this is a 1995, Microsoft Word. Thank you very much.
No, I meant you must have had some implementation, right?
Oh, I had implementation. Oh God. Holy shit. That implementation was kept at Rice University for years upon years, because I moved to Sun and my directory got folded up and put into cold storage. And then Java became hot and excited, and Sun wanted to have an official copy. And I said, you can use my shit, and I'm using it directly, but my name goes in it. So in the core guts of the C2 compiler, it says, some of this code is courtesy click, and there's a file name mentioned, which was fucking opto/tg.tgc. So opto was the name of the directory I used, which turned into the name of the directory at Sun for many, many years. I think a C2 showed up in there somewhere. But for a long time, it was called the opto directory. The core JVM implementation was opto directory. Same as the file, opto.tgc, tar gzip from 80s, right? That file then became like hot shit when Google came around and Oracle bought it, as evidence that courtesy, some of the shit was clearly labeled, Creative Commons, open source shit, do what the hell you want with it. Let me see if I can, I wonder if Google will find it now on the Wayback Machine.
I'm not sure that looking into the code is the best way to get the basic concepts.
That was what I was coming around. Yeah, I can't find it with a simple Google search, just straight up. So fine. Yeah, I was worried that it was not necessarily the best way to get the concepts. Yeah. There's some depth to there. I can run through some fields and I'll show you one-to-one mapping between what you're seeing here and fields that make sense. But going into how the code that does it all and shit gets deep fast. But things you see here have a one-to-one mapping to fields I have in the IR.
Yeah, in practical implementation, there will be a lot of details which are not important for the basic understanding.
Yeah.
And it will take a while to
Right. So if I come through here and ask the damn, there's a way to get just the field names out of somebody here. Here's a pile of them. Okay, let me show you a quick set of core fields. And I'm missing the def field. Let me grab one more field after this. I'm going to throw this in the nested to open windows. Here we go. Boom. Opposition question I'll get to. Somebody's got something else going on. I'll touch your opposition question in a minute. Let me go add fields to where the hell I'm going to go back up to block for copy. I got a bunch of things here. I'm going to go. No, that's the wrong here. Here's where I said apply. After the apply in the middle somewhere, I don't know where, whatever, fine. Here's a set of fields with, comments. You're missing the defs and uses. Let me go find that. Why are you here? Here's this guy. So 2 other fields of excitement here. And the other one will be just uses. Okay, so let me go explain what these fields are really quickly. So public int UID. So let's get rid of public and shrink the font a little bit and get things lined up here. So it's maybe, I'll leave it like that. No, let's shrink it once. So public int UID, I get it to not wrap, that's good enough. What it is I've named all my nodes with a number so I can easily look them up in tables. I use bit vectors on them. I can hunt for them. I can tell them apart. It's created upon construction. This is a Java implementation. The constructor just says UID equals global counter plus plus. Okay, opcode. There's a short, dense runtime thing. There's actually a vtable. It's a Java. There's subclassing, but I threw an opcode byte in as well because it was convenient in some places. It's really optional. I could throw it away without really any great harm. There's an array vector, a vector array list, however you want to call it, of defs and uses. The defs are ordered, the uses are not. The notation here, that array ARY guy, he's just a doubled array. He's just a Java array list with shorter syntax and a few more convenient functions I have that the array list does not. With so
defs are what? Are they so? Defs are stuff that's been defined in this node?
No,
because normally in a basic block you have defs and uses, right?
Yeah, we're getting there. So it's no basis per node. Defs are what is defined for this node, what this node will consume then.
Basically, operand of this node or this instruction.
It's say it again. I missed.
It's operands of this node.
Yes. It's not what this node computes as an operand itself, but it's the operands to the node. So if I look at an add of 3 and 5, one of the defs will be a 3 and one of them will be a 5.
So this corresponds to on the paper, you've got node inputs, right?
Yes, these are the inputs to the node, yes. And the uses are things that use this node. So the add of 3 and 5 is used by a call to printf. It's used by an if is equal to 0 or less than 10 or something. This will be the uses is
in AST, uses is parent and defs are the children.
Yes. So you notice that it's kind of inverted because an AST is kind of upside down compared to how I'm drawing the graph. I'm drawing the graph in the order that you would execute it mentally. But that meant that if I come down to a node that's low, he's pointing back to somebody that computed something before he got to it. So that's his def is up, whereas in AST, it's reversed going down.
So in the paper, you just had inputs, but here you have defs and uses.
The uses are there for the optimizer, and they go to the linear time of people roles of optimistic, pessimistic optimizations. They go to the linear time.
So are they optional? Like
they are optional if you want to have semantic meaning, but you're not caring to do optimizations. So let me be clever here and say something I did as a cool hack that's not necessary. In the land of C2, when I parse Java bytecodes and I produce nodes that I'm going to optimize immediately because you get a huge count of redundant if checks and range checks and shit going on, I don't bother with uses yet because the unparsed program has an unknown number of future uses. So for a while, the C of nodes IR as done inside hotspot has defs, but no uses. That field is null. And then I will add the uses when I'm done with the parser because I just don't know yet what the uses are going to be. Okay, so I'm going to move elock down because it's an engineering debugging hack and has no semantic meaning. I have a value field. The value field tells me what I compute as a type, as a set of values. So integer is a set of values representing plus or minus 2 to the 64, and everything in that range in the middle. 17 is a type that is an integer of just the 17 guy. String hello is a type. String hello or null is a type, and so on and so forth. So this is all the possible types for value. Control and X control are types. So is that, we understand what a type is, basically? It's a classic, I'm using it in the set of values type notion of what a type is.
Can we include it in the presentation mode because we're still on paper?
I'm showing this in the, oh, yes, let me, thank you. I will do that.
No
I'm sorry, that's a good answer.
I got your back.
Thank you. Okay. Yeah, right. So the value field is just the set of types that might happen here. There's a special all type and an any type. And the all type is like the error case. It's like the worst possible. I know fucking nothing about this. Maybe it's control flow. Maybe it's a string. Maybe it's a 17 or pi. Maybe it's God only function pointer. I don't care. I have no clue. And any is the most optimistic version where I start the optimistic guy at and things fall into more specific types, the most general type. I'm sorry, most specific type. Shit. Any is the canonical most specific type. It's more specific than any other type. Okay. I compute liveness. This is the inverted version of value, if you will. It's what is used from this guy, and it is not necessary for anything to do with C of nodes. I've added it in AA to let me define programmatically that a value is never used. So in the typing of the world, I can say this value, I don't care what his value type is. It could be an error. All is considered an error type if he's dead. So I have to have a hard algorithmic solution that I can run that says this is not live. Separately, the optimizer kicks in and may discover more things are not live later, but at the typing time, there is a known canonical, this was what it means to not be live, because that it means the program types or not, because you have a typing error that is also dead, and I don't care what it is. So there is a liveness field here. And it waffles between any and all and has precision when you have a type that has internal precision, such as a structure type where you have fields. Individual fields are live or dead, and the liveness picks that up. If you threw that away, it would change nothing that you're doing here. C2 and hotspot does not have this field, it doesn't need it. He does a grosser version of liveness where he just says, you have no output edges, therefore you're dead, and therefore when I do I count your output edges and they went to 0 thing, you got deleted. There is a type variable under the classic Hindley-Milner typing that's new in AA as well. This is me doing Hindley-Milner on AA. TV2 is because I had a TVAR and I had a TV1, I had a TVX, and I had a TV2 as I went through implementations and failed out and finally got it right. Okay,
so we can say that you embed the Hindley-Milner type inference into the sea of nodes representation.
Yes, I'm embedding Hindley-Milner type inference in the sea of nodes. This is exactly the Hindley-Milner type for this guy. And when I run my big typing analysis hack thing, you magically get a highly precise Hindley-Milner type variable for every node.
Which is absolutely interesting.
That's part of, what I consider my gain, my useful, productive work in the last 2 years is this integration of Hindley-Milner and forward flow value typing in a useful, meaningful way. I get an optimistically better answer than either alone.
I believe this is absolutely cool.
And then elock is me fixing bugs within assert. So I do this hash consing thing, which is 2 nodes are equivalent if they have the same edges and the same opcode. They compute the same value then. That's all your dependencies are all tied in your edges, including control edges or anything else. So I compute a hash code for you based on your edges and your opcode. If I change your edges, your hash code changes. And so many bugs come around because I just did a graph rewrite rule that changed edges on somebody who, because the graph was a little bit bigger than just your nearest neighbor, and the rewrite rule was a little more complicated, and I missed telling a node that your edges just got changed. You need to get out of the hash table under the old value of your hash code, and then recompute and go back in on the new hash code. So the
When you
ELOC
say
was
edges,
just
do you mean the defs and uses?
the defs, not the uses.
So that's included in the hash code of
the hash code is
of each node.
Yes, the hash code is the hash of your inputs and your opcode, and your inputs hash is their UID. It's their unique. What the hell they
But
are.
equality is just based on UID, right?
The equality, no, the equality test is two nodes which have different UIDs, but their inputs are the same UIDs and their opcode's the same. So an add of X and Y and an add of X and Y, they're two different adds, but they point to the same X and they point to the same Y. I hash the UIDs here and I hash the Ys, and they're order dependent, so I hash them in order. There's an order to the hashing, and I hash your add code for the add. I get the same hash. Now I do an equals check. The equals check is just what you said. It is edge matches edge, pointer equality for the two inputs for X and pointer equality for Y, and opcode equality for the opcodes. And then you're done, you're equivalent. And the people engine core, I haven't showed you the core people engine. He has a series of steps he goes through. One of them is he does this hash. And if he finds a hit,
so is it like every time you create these new nodes, you check for if it's already there?
Yes. This is the speed of C2. One of the speed hacks, I talked about it last week. One of the speed hacks is I pull a node from hot storage that I just had things in a second ago. However, I get that hot storage. So I have an arena I'm bump pointering on. I pull it up. I fill in the input defs. I fill in the opcode field. I compute the hash. I look at the hash table. I get a hit. Okay. I tell the parser, use that, not this thing I just made. And then I push this thing back onto the hot storage for the next go round.
So does it mean that every node is also in the hash, like hash table?
So every node attempts to be in the hash code all the time. Periodically, they get thrown out because their inputs changed, and they don't immediately get thrown back in because it doesn't happen that I need them immediately. That's an optimistic cleanup. That's I'm going to get to you eventually. And if your edges are changing rapidly, I don't need to keep rehashing you in, hash you out, hash you in, hash you out while I whack your edges. So the ELOC bit, it says you're in the hash table or you're not. And when I do an edge hack on you, I stop and look at ELOC. And if you're edge locked, that's what I call edge locked, then I pull you out of the hash before I change your edges, so your hash is correct. Then I clear ELOC and let the edges get hacked. And I threw you on the work list. Later,
so if you have, say, an expression like A plus B, you would look up that in the hash table to say, do I already have A plus B?
Yes, it's called value numbering. Because I don't have control edges, because things can move around. It's actually
and you don't do that later on. You just do it as you're building the nodes.
I do it as I'm building, which is also identically the same as I do it after I'm done and after anything happens. The pessimistic people optimizations use a work list. If the work list is empty, there's zero cost. If something changed, I pull them off the work list and go again. If value numbering works, I lose a node. I get rid of a node. So it's a monotonically improving situation, but it's also extremely cheap to run if there's nothing to be done. So I run it all the time.
So quick question. Most nodes start with a single node in the uses list?
Most nodes start with the use list empty, and then the parser points to the node, which I have gone back and forth on that implementation in the current strategy.
Right, you patch it up after the parse, right?
That's the C2 version. AA does things a little differently, but it's not too, it's a little easier mechanically to do what AA is doing and no performance change.
Right.
As
but, conceptually, I mean, yes. Forget when you patch it up, but conceptually, when you create a node, it has one use.
It has only the use by the parser, yes. I just said X equals A plus 3. I did A plus 3. Let's start with that one. A plus 3. I put a node of the plus. Who's using it? No one in the yet unparsed program, because I haven't told you any of the context around that.
Because you haven't said x equals yet, right?
Because I haven't said x equals yet. Yeah, or maybe it's
Right.
just
So
passes an argument.
as
to a
you
call.
return up through the recursive descent,
Yes.
you will bind the
Yes.
parent to the
So-
child, right?
Right. So the parser carries the current active node for the expression as the return value from every layer in the parser. Like the parser totally matches the AA syntax function for function. If I said you did
Yes,
an if,
understood.
Yeah.
Recursive
Yes.
descent, got it.
Recursive. Okay, then yes. So there is an implicit implied use of every original node by the parser while I'm parsing. And then how do I
Okay.
mechanically do that so I don't accidentally drop you on the floor and declare your count went to 0
Right.
and shit? And that's waffled back and forth between what C2 does and what AA does a little bit. Where I'm doing it right now is the parser actually has a real node called the keeper node that keeps nodes around. It represents a use that you don't know what it's going to do eventually. And eventually all the keeps go away. But I hook you once by another node. So your node
Yeah,
count
I
never
do.
goes to 0.
I do on the recursive descent, I never have the back pointers. So what you call the uses.
Yeah.
And then after the recursive descent, I do something called introduce parentage or something like that. You know, so basically it flows through the entire tree, the back pointers.
Yeah. Yeah. I mean, I've done AST based versions and similar behavior goes around. Yeah.
In
So
A,
when do you see the uses go from 1 to multiple? Is that just because of the deduping? Like, so you end up.
No, you get multiple uses because the parser has used that value again. The usual one is I said x equals a plus 3. And at the time I said x equal, the parser picked up a mapping from a textual string x to the node for a plus 3. And then the parser doesn't keep a plus 3 around himself, but he has a mapping for the x equals. He does keep it around. Now, every time I say x, I use x and use x and use x and use x. Every one of those x's point to the add for a plus 3. And you start picking up uses of the add of whatever, the plus of a and b. And so I see the confusion.
Is
So
it like
Yeah,
every time you
I
look
didn't
up in the
follow that.
hash table and you find something, that's a use, right?
no, the hash table is for global value numbering. It lets me find 2 identical nodes and replace them with 1. Common sub-expression elimination. That's what it is. What I'm talking about with Cameron is a different scenario. I have made a node during parsing, add of a plus b. I've assigned it to x. The parser maintains the state that the identifier x maps to an add node. So he has a mapping literally from an identifier string to a node. It's a hash table map, but it's based on the identifier string. Later, he parses another identifier x. Because the scope hasn't changed, it's the same hash table, it's the same map. He looks up x in the hash table, comes up with an add. That value is now on the active parser's recursive descent stack for the current expression value, which then goes into whatever that expression next happens. Somebody says, multiply x by 7. So he's a multiply node, which picks up a pointer to the add node and a 7 because I did x times 7. And every time
So
you
it
say,
doesn't point to the X node, it points to the.
there is
thing
no
with
X
the
node. There is no spoon.
Interesting.
There is no X node. X is a name, as an
Right,
identifier name. It is mapped to a node. You only point to the nodes when you're done. There are no names. The whole point of this translation step, and this is last week's thing, is I got rid of the names and I only have nodes. Let's go do that. Dun, 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 dun. Here, this guy, let me share you. Okay, this guy, let me go to actually the much simpler guys. Okay, well, even simpler yet. Here I am. I'm doing dist is equal to blah, blah, blah. There's an X. That is where I have mapped, but this is not an X node. This is the computation that produces the value for X. And I only have the mapping from the string, which I highlighted at the bottom of X in a hash table map to the node. This is just me being convenience on the graph. There's nothing in the IR that says X. The IR has no X. There is no spoon. So when I
And
roll,
this map, is this like a symbol table or something like that?
Yeah, totally the symbol table. This is the symbol table, yes.
And is this like scoped, like it's in every scope?
That's correct. So as I roll forward, parsing, so my green arrow is pointing at X, I'm parsing an X, I look it up in the table, I put it on the expression stack. So also in the bottom, you see the expression stack pointing to the node that represents what X is being presented by. I parse, I multiply, and now I do recursive descent. And this isn't a recursive descent talk, so I don't talk about what I'm doing with recursive descent, but do some sort of recursive descent to save the multiply around and go forward again. And I parse another X. Now I have two X's on my expression stack at the bottom. And then I'm done doing the operand X parse because we're recursive descent precedence operator said I'm done. So I take the two values that multiply needs, I pop them off my stack, I build a node multiply, I use those two edges I just pulled off the stack, and I shove them in the node. And then I push it back on my expression stack. Oh, Aaron.
So do you have a node for a variable? No, I guess you don't.
I don't have a node for X. I have a node for X. I have what X gets me, but I don't have a node that is the X node. I have a value that X is being computed as. So suppose earlier I didn't show what X got computed as. But so somebody said earlier, said X equals 7. Then this node would be a 7. Because somebody says X equals 7 earlier, and I just had a computation for it. So the blank here is saying, whatever you got X from, I read X from standard in. X is the return value from the read call. Let's see some, I only get 5 people when I do this share screen, so I can't see everyone's blank stares. All right, I'm gonna go forward and then, because I'm just gonna repeat myself for Y. So save the plus for later, same operator precedence thing, I don't know, save it for later, we're not talking about it. Do Y, look it up in the table, put it on my expression stack. I left the other guy expression on because I'm building a bigger expression, so it has a couple parts to it. Save the multiply, find the Y, push in stack, pop the multiply off my operator precedence table, however my recursive instance goes, take 2 nodes off, shove in the multiply, push back on the stack, repeat for plus. In the operator for plus, pop 2 off, build a plus, point to whatever the stack had been pointing to, push it back on the stack. Now I'm going to do dist. Things get a little different at dist.
Yeah, when I saw this last week, I didn't understand what map was, but now I understand it. So it's symbol table. It might be useful to rename that to say it's a symbol table.
It's a symbol table, but I'm going to have a bunch of them, and writing symbol table everywhere gets too complicated. So I could open up by saying I need a symbol table, and that's a fine thing to do here. Map. Name to node.
Otherwise, it's not. It wasn't clear to me what it means.
Yeah. Well, let me do this. I have several of them. It's a map from name to node. Now I clean up my slides in a bit there. So I'm back to here. I'm about to do dist. So what the parser will do now is he'll take whatever's on the expression stack and make a new mapping in the symbol table from dist, the string, to the computation for it. So I didn't write dist on the slides like I wrote X on the slides. And I'm trying to get people to think that it's not, I'm doing it now. There's no dist node. The name went away. That's the point of this parser, is to get rid of the names and only have nodes in an IR, have SSA. But that's the computation for dist is right there. But there's no dist node in the graph. There's a map from dist to node. And I will typically call it, hey, see you, Chris, the dist node, because that's the mapping. I'm just speaking out loud, but there is no special node for that has, there's no node in the graph that says has the string dist on it. That's the key. All the names went away. The graph has no names. There is no spoon.
And the region nodes, are they like basic blocks in a way without constructing a list of the instructions inside?
Yes, they represent the head of the basic block. It's the input merging that you would get for a basic block, plus also the start of the basic block. So
you're not maintaining the list of instructions because anyway they are linked.
That's correct. This is the sea of nodes where nodes have no control flow. They float around other than the edges you see. So if I whip through, this one is a bad example because I didn't merge anything within the true and the false arms. But let me go look at the control flow of the loop. All right, see you, Dan. Here's the loop. And my symbol tables, my symbol tables are on the right. I've cloned one for the head. I've got one for the loop I'm going to parse. They're the same at the moment. I threw in my fees because I don't know what my back edges are going to do yet. So my fees have a blank, unknown, yet pending back edge, whatever it means. I put a computation down for less than 10. Okay, right now, at this moment, there are no uses of less than 10. If a use were to appear on the printf side, I could float that out of the loop down to the printf and print the Boolean value less than 10 outside of the loop. Because not yet has the parser discovered that there is a pending data dependency to force less than 10 in the loop. So I threw it in the basic block because this talk was originally about how to build SSA and not about sea of nodes. But in fact, the edges you see are the only edges that guy has. And he will be bound in the loop only if he has a use that binds him in the loop. And if he doesn't have a use in the loop, he doesn't have to be in the loop. And he doesn't know, he can't even tell he's in the loop. He doesn't know what fucking basic block he's in because he doesn't have any edges on him that say what basic block he's in. So on purpose, he could be anywhere as long as he's got the fee that he needs as an input and the 10 as he needs as the other input. And that's sort of the C in the sea of nodes. So as I move the parser forward, I pick up another add, again, node dependencies that bind you in the body of the loop. But when I hit to, oh, again, node dependencies that bind you in the body. Oh, no, I'm sorry. Boom, boom, boom. Here, yes, here when I side, I don't have an edge for it because I didn't on purpose. When I tied the less than, it just has to have an edge for this discussion. When I tie the less than to the loop exit, you know, I don't know how to get here. Give me, give me this. When I tie this to the, here we go. This is what I need to do. Yep. Try again. Let go. Go to here. There you go. And it's reversed, so I have to reverse it. Let me, what? No, I want the connector. I want the reverse. I want the line, I guess. Maybe line. Yes, I'm backwards here. Okay. So when I add the edge to the exit of the block after 20 minutes of trying to fight with the damn program, that's the point where I'm bound into the loop. When I don't have this edge, I'm not yet bound to anywhere in the loop. I'm below the fee because I have an edge there, but that's the only dependency I have. When I pick that one up, I'm stuck in the loop. Actually, I had the direction correct. Oh, fuck. Fine. Because I'm doing use step edges. Oh, you died again. Here it goes. Fine. Okay. So is that, I mean, it would make it worse or better by having that discussion. When I do the sea of nodes, I have a node there, an if node. The end of this basic block in the sea of nodes has an if node. The if node takes a predicate as an input. And immediately I'm now bound into the computation for the loop. So I can go back to the IR95 paper where I have a clear presentation of that. Okay. So in this one, there is a region ahead of the loop. There is a test, which is your less than 10. It's depending on I, which depends on the fee. Okay, so it's a little different code, but it's X less than 10. It's +1 of X less than 10. There's an if, which takes it as an input. Here I'm showing def use edges because that was the normal at that time. When I program it for the last 30 years, it's always use def edges, so I draw them the other way now. But def use edge from less than 10 to an if as on his second input, which is his test input, his predicate input. Now I have a loop formed by the control flow from the region, points to the if, points to the true projection, points back around to the region. And the test here has its input is on the fee. I'll highlight the fee. If I can highlight the fee, which has got a control input on the region. So the fee is stuck to the region. His entire semantic meaning is tied up. The select there, the fee is tied to the region. His output goes to the add, which goes to the test. I'll try to highlight it again, which goes to the if, and he's stuck in the loop on his edges alone. So when I do layout, after all optimizations and analyses are done, I do layout games. The layout guy pays attention to the edges. He's forced to put the +1 less than 10 in the body of the loop. So is that? See some yes, some no, some
yeah, it was helpful. It was helpful.
Okay. Okay. So I'll go back to the other presentation. Okay. And at this point, I'm going to roll forward because I now have the sum of X and sum as a value the parser has discovered, but not yet found any uses on. So that add is very obviously not tied to any loop at the moment, but I don't know yet because I haven't found all my future uses. So the parser is keeping it alive, but you know, it's flexibly wise, or where I compute it. If I compute it before the if test, after the if test on the back edge, like if I do a proper layout for this loop, I probably want to put that add before the if test, so I don't have to have a double pieces of a loop with a, you want just a simple, straightforward, empty back edge. If you have a back edge that has shit in it, you get an extra basic block and it doesn't run as fast. So here's the +1 on the X. Again, not tied to anything. For the uses of the add nodes, the two add nodes are free floating going down. They could go up only as far as the fees they pinned on, but they can't go down, and they could go down as far as they want. When I go around the back edge, they pick up the use in the fee, and now they're bound in the loop. They have an input edge that comes from before the fee and an output edge that comes after the fee. They're stuck in a cycle, they're stuck in the loop. They could still float around between two different apparent basic blocks. And in the sea of nodes, there is no apparent basic block separation here. And I can't tell, don't know, don't care that they're floating around until I do placement of, you know, reversing the sea of nodes into a real control flow graph with things placed. But that happens right before CodeGen. That's part of CodeGen.
Yeah, the one thing I don't get, you may just be reading this wrong, but the less than points only to the head fee.
It points to the head fee, it points to the 10. The if, which I'm not showing in the sea of nodes, points to it. So I'll add that node in.
Right, but the X changes in each iteration.
Yes.
But it still only points to the head fee.
Yes, the head fee takes on a continuous set of new values every iteration of the loop.
That's probably what I'm misunderstanding in the graph. Okay.
Okay. Fees represent, like, if okay, hang on. I'm gonna go roll backwards. Okay, right up here. What value does X take on? Okay, X is in a loop. For X equals 0 to 100.
Yeah,
blah,
but
blah, blah, blah.
this is why it's handy to use name nodes, because you don't really care. X is X. Whatever X is in this scope at this point, it's X.
Okay. The reason to use SSA is so that I get all these things we've been talking about with cool optimizations and understanding what the hell's going on. The value for X in for X equals 0 to 100 is represented in SSA by a fee that takes a progression of values from 0 to 100. The compiler can't execute your program one line at a time. It has to do an approximation. So it says, oh, you're some integer value from 0 to 100, or you're some integer, whatever your approximation of choice is. So when I come down here to the loop, and I'm asking a question.
That fee then represents all values that the loop would experience.
For the X, yes.
For the X.
And the other one is all values the sum will experience.
Okay. Okay. No, that's what I was misunderstanding. Okay, got it.
Okay. Okay. I mean, that's sort of, you know, the next piece I would do on my if here is I'd add true and false nodes, and I'd replace the basic box wrappers with nodes that represent the box wrappers, but done with nodes in a graph, and you'd see
Do you
they
have
line
this
up.
presentation on Dropbox by any chance?
Yes, this, and I gave a link out last week. It's on YouTube links channel. I can throw the link in again. I gotta go find the correct link, which is not here. It went to presentation 2022, easy SSA, PDF, copy Dropbox link. Here, where's the link section? Boom, boom. Okay, there's the Dropbox link for easy SSA.
So is it possible to say if I have a linear IR with basic blocks and instructions, etc., can I transform it to sea of nodes?
Yeah, just the same as you transform an AST to sea of nodes or AA or the stuff I'm showing here. There's some parse-like behavior. When I parse Java bytecodes, it's conceptually extremely similar to the parse that I do here on C-like program text. But the names have all changed to protect the innocent, if you will. But it's the same damn schmick. You parse a bytecode and it says something like, I take Java register 1 and Java stack element 2, and I do an add and I push the result or whatever. I perform those same actions in the parser line by line by line instead of a recursive descent because you're complicated, building the graph as you go. If you have nodes in a CFG, you have tuples in a CFG, you can totally do this translation. And in fact, if you're building SSA form in a CFG, you do half of it already. The only half you have to do is to get rid of the mapping that binds you to a basic block. You throw things away and you build SSA instead of just building SSA.
How do we keep track of the things we can reorder that are pure, their order doesn't matter, and there's and those that have side effects?
Okay, exactly, and only edges represent ordering constraints. If there are no edges between nodes, they can be reordered. So now you said side effects. I put side effects directly in the graph. So let's go back to the other presentation and I'll show you side effects.
So side effects have to be edges, otherwise they won't be ordered.
And yes, side effects are done with edges. So where's my my load and store? Let me find my load and store here. I just had an example floating around. Yeah, here's a load and a store. Okay, middle of the page, figure 6. So there's a memory edge. Stores take and produce a memory edge. This and loads take a memory edge, but don't produce one. Memory edges merge at fees like other values. Memory edges are arguments to calls and return from calls. That forces stores to order by the memory edge and forces loads to order around stores by the memory edge. Outside of that, there's no other constraint on the ordering for memory side effects because all your side effects are now explicit in the graph. So you normally put loads and store nodes in a standard tuple IR with basic blocks. All I'm saying here is, oh, pick up an edge, which you would have edges by however you do the names in the tuple IR. I have an edge for memory as well. But then I'm free to reorder things based on the edges alone.
So alternatively, you could have represented this dependency as control edges and have like a separate analysis to reorder this control dependence based on aliasing properties.
Okay, so right. So I have control dependencies to force other kinds of things like divide by 0 or load from a null to prevent reordering of things that throw exceptions, really. There is an abstract IO for things that call off to things that represent unknown IO side effects like fire the missiles, write to standard out. But for memory alone, I do it this way because I can now go to the next step of saying, I can split all my memory edges into equivalence classes. And well, I have papers that show that if you split by the obvious dumb equivalence class, you get 95% of your best Oracle aliasing improvements that you'll ever get. But the split by equivalence classes is essentially free.
So, but this is not like it's nice and convenient to have in your IR, but in theory you can do without it. Like, for example, in GCC and LLVM, there is memory SSA analysis, which is built on the side and does basically the same thing, but it's a side construct and it's not embedded in the IR.
Right. So what I've done is I've said, everything's in the IR. It's super easy to add nodes. It's super easy to add edges. So it costs me nothing, no separate pass, no separate analysis to throw the memory edge in. Now, all my other infrastructure for doing optimizations is unchanged and also now doing memory without any extra work on my part. The people engine that says, take things off a work list, apply people transformations, put their neighbors on the work list of progress, repeat until done, that's unchanged because I have memory edges. It does the same thing it ever did.
Well, but then the cost of it is that you need to maintain these edges as well as other kinds of edges when you rewrite the graph.
Here you fell into my trap. Edges are fucking free. Okay, not quite. They are so cheap, it does not matter. They are literally a pointer.
Oh, I mean, when I say maintain, when you write a transform, now you need to rewire the memory edges correctly. Otherwise, you will have like subtle miscompile.
Yes, you do. And only store and load node people transforms care. All the other transforms have no fucking clue. They have no memory edge. They see no memory edge. They don't care. They don't do anything. Nothing happens for them. Only, and actually loads don't actually edit any memory nodes and memory edges. They only check them for equivalence. Stores can reorder and hack memory edges. That's the only thing that hacks memory edges. So there's people rules on store that say, look at my nearest neighbor and see that I'm back-to-back storing some value over some value. I'm going to rewrite and get rid of the earlier store and just take the last piece. Or something like that.
Do your calls have memory edges?
I'm sorry, do what?
Calls.
Yes, calls have a memory edge. Calls don't do much except inline as a bulk thing. Otherwise, a call is just like an unknown point. Call says, I took all your memory, I produced all your memory, and fucking, I don't know after that. And then if I want to get more precision, I'll inline the call.
Yeah, the way I view this is essentially you cached another analysis in the IR.
Yes, I did.
Now it's easily available, but you need to update and invalidate it.
But you're missing is that, yes, I'm updating it and validating it, and I'm already updating it and validating, doing the normal graph rewrites that I do already. I did no extra work to maintain that memory edge, except when I looked at a store node doing a peephole, he had to pay attention. No one else did anything, and that memory edge is just maintained for free. And that's the trick. I do nothing to maintain that memory edge.
Yeah, well, and any load optimizations have to limit themselves not popping past the store.
Well, but I do nothing there. That's a standard use-def dependence edge. I have to, I'm already, every node has that same property. You have to honor your use-def edges. Same as a load honors his use-def memory edge like every other edge and every other node. I do nothing new for loads to honor their memory edge. So
I'm not critiquing this approach. I'm just like exploring other possibilities or how things are done in other
I'm telling you, C2 does a fucking fine ass job on memory analysis optimizations for essentially nothing. I can do, value numbering on loads with memory edges works just the same as value numbering for all other nodes. So redundant loads get eliminated by the value numbering call. I did nothing special about loads to make that happen.
It does feel that there is a win representing.
That's the trick. I mean, that's what I'm sorry. I've had this conversation with interested compiler people on and off for 30, 40 years. Handful of people take me up on it and go to town, including the Grail group. Not everybody does though. So, I get excited when you're excited and you start to see how it fits together. It does all hang together super well. Whether you buy it or not, I don't know.
Okay, I'm sold. I will run.
There is a project called libfirm. I don't know if you know. That says they implement C of nodes.
Okay, like I said, a handful of people. I don't know. I haven't heard this one. I throw a link in somewhere. I'll take a look. I'm curious now.
It's they have. And they have a nice visualization tool as well. So maybe that would be helpful.
On and off throughout the years, a bunch of people have done nice visualization tools. I find they're not helpful except when you're first getting the holistic concept down. For day-to-day debugging work, they're just not helpful. I've had them, 3 or 4 of them got written out of people who came out of Sun. I know the Grail group's got them. I find them personally, like I said, not terribly helpful.
So I pasted the link to libform.
Yeah, sounds good.
They say it's completely graph-based source and target intermediate representation, CF nodes.
I will take a look when we're done here. Somebody had a question. We're getting on, so I'm going to look see if there's optimization question. Is that particularly who asked, or what are you trying to ask here? Somebody's grabbing a value out of a closure. They're trying to discover I is 5. They're trying to return it.
Your code is at the end of the docs, of the Google Docs. You asked the question.
Well, there's another Lua one further down.
Yeah. So I don't know if there's somebody else before me, but yeah, I have some questions.
Okay, I'm looking at the optimization question. It says optimization question.
Okay, that's mine. Yeah. Okay, so a while back when I was last on this session, I talked about this thing that I was trying to solve. So the code, the Lua code is above, where you can see that you have a local. I don't know if we can share this.
I can. Google Docs, just a second. If I find my Google Docs somewhere. So I'm looking at the hybrid Lua C and not the optimization question.
This is later. So if you scroll up, I think it should be.
Yep.
Yeah, this one. Yeah. So yeah, this is one optimizer. So here you can see what I'm trying to do here is that I'm just going to describe the Lua code first. So there's a local variable I equals 5, and then there's a function being defined called foo, which returns another function, and this function references I. So my goal here is to say, okay, well, I can see that I is a constant, and this is called an up value in Lua. Basically, you are referring to something in the stack, which is in your parent function. So then it becomes a closure, right?
Right.
So here, what the optimization opportunity is that I is a constant. So there's no real need for it to be an up value, right? And so the generated IR is shown below. And I've highlighted the section that's of interest.
Right.
So
I totally get what you're trying to do here.
So here, on the left-hand side, we have return. So the original code is return up value. It gives you an up value reference, and it's now been replaced by return 5 constant, right? Which is the optimization.
Right.
So now I did this, but I kind of did it in a hacky way, I guess. So I wanted to understand, this is very similar to how in a C program, you might want to optimize, say, static const values, right?
Yep.
But the way I've done it is that in the AST phase, I mark each symbol as being initialized if it's got an initializer, because I need to detect whether it ever gets modified after the initialization.
Yep.
So in the AST phase, I basically mark it as initialized if it's got an initializer, and every time there is an AST which would change its value, I set a flag saying it's been modified. And therefore, later on, I generate this IR first on the left-hand side, and I have a pass which runs through this IR and replaces any reference to a symbol which has never been modified.
Right.
And it basically says, okay, this guy has never been modified, so I can substitute the up value for the actual constant, right?
So
I think this is pretty hacky way of doing it.
Yes.
So now what I wanted to know is what's the official good way to do this?
So in the land of upcast functions and functions that have closures, I don't know if there's an official goodness. I did it a particular way, and only for AA, because Java doesn't do this or didn't do this at the time C2 came around, and instead does rewriting under the hood. And the thing I'm doing for AA is the function, the inner function f takes a hidden extra argument, which represents the outer scope. The outer scope has an assignment as a store of a 5 into basically a frame, and then a load, and those are loads and stores. And I can see via the load and store math that there is no other modification other than the original store. So basically I have a load that loads from a store. When I hit the return I in your function, I have a load. It points to a parameter to function, the inner function, which if it's only called in this context is only taking one internal argument, one argument, which is the context locally, which is I equals 5, which is a store of I5, and then the load lines up and says, you're a global static, so that's a particular namespace. That I is this I, because it's a global static. This is known by the parser. Therefore, this load points to the store. I do a load store optimization. I clean it up, and you get whatever the value was. So 5 or whatever you computed there. So I said a bunch of things because you're showing an example that has other issues were there to be other code floating around. And I'm carefully describing a solution that works in the most general case, but then optimizes in this case. So the most general case is I run foo, I get a function back, I execute it in another context where I got set to something else. And I want to find the last assignments to I that's valid at the time I call the return from foo, the function. I call the return from foo, which is the function that returns I. So somewhere in the world, I'm threading through the local assignments to I as loads and stores on a frame. Somewhere I have a value I return from foo at some point, who's now hooked as a hidden extra argument, the frame at that time. Then I load through that frame. If you use the function, the inner function in this kind of a way, you'll be forced to malloc a frame or do somehow have you'll have to have a hidden frame. If you do not, then you can totally get away with, there's only one frame, and I'll just take the last value that I got set to as what I'm pointing at, because when I point to a frame, I point to a load off of a struct that's a store, and I'll just find the store from the load, and I'll get whatever the value is. So right, so here you go along and you say, oh, I've declared, but I haven't run foo, so I have not yet captured the value for I. So let me go make you the bad case. So this is the good case. What you're showing here is basically the good case. Oh, let's do the good case first. We do the good case first. Somewhere in here, I'm going to say sys.print of, well, I'm going to call foo. That's going to return me a function. I'm going to call that function. That's going to return me an I. And I'm done. That you would like to fold down to a 5. So let me go shoot a bad case here. Baz is equal to whatever I get from, calling, I don't know, Lua syntax. I call foo. I got now an upwards exposed funard capture of I is 5. Then I say I equals 10. Now I say sys.print of Baz executed. What do I print? Do I print 5 or do I print 10? What is the semantic meaning here of this program? And then that dictates how you have to declare what it means to have an inner function with an upwards exposed funard.
Should it print 10 because that is the last code.
As far as I know, it should print 5.
No, so in Lua it will print 10 because when you've captured that, when you reference a variable I, it's basically still referring to the I that was there over there.
Okay.
And so in this case, what my code does is it says, oh, hang on, I got modified, so I will not do this optimization.
I got it. In my version of things, I'll say Baz as a function gets handed an argument, which is the current stack frame. He looks up I in it. So he has a load of I off of a parameter that got passed in. There's only one parameter getting passed in, so it's always the same parameter. So it's the constant current frame. So he does a load against the current frame, which has I as 10. So he optimizes and says, you got a 10. It's not I give up, it's I got a 10. And that's because I did a series of people rules, one of which says Baz is only called with the current frame. That current frame is an argument with a single value that comes in. It changes whether it's I5 or I10 or whatever, but it's a frame as a struct. It's the same struct every time. So I don't need the argument. I'm gonna throw that argument away and just globally hand you in the local frame. Now I have a frame, which is a struct that I do a load on a field, the I field in it. Previously, there was a store of an I field of 10. The load knows to peek through the result of a struct, which is actually a store. So the load peeks through a store and finds the matching store for I is 10. The struct is actually a group of stores. It's the last group of stores for define the current value of the frame at the moment, you will. So he looks through and finds the correct store, and then he says, I'm peeking through, you're a 5. So there's a gather and scatter piece I didn't talk about before for struct that I'm doing.
Sure. So I think what you're saying is there's no standard way, at least for this
Not that I
kind
know
of closures, right? But what about, because I was thinking that it's very similar. This code looks very similar to, say, C code, where I is a static const.
Yeah, as soon as you said global statics, you can shortcut my hack and say, it's a global static. I know that. I don't need to do the piece that said, I took a frame. Oh, it was the same frame every time. I don't need to take this frame because it's the same up one layer frame. I can use it directly. So I can get rid of the passing of the hidden frame argument and say, you're talking about the global scope. So now I have loads and stores against the global scope. It's a frame object like thing. It's a struct like thing. The global scope is like a struct of all the global variables. And I do a field load against it. And I go find the correct store that produces the same name field. And then, line up and say, oh, I'm loading the last thing that got stored on this field, whatever that is.
Sure. So
I go from no constant propagation to being a value equivalence. I'm getting the value, not the constant.
Okay, and how would a traditional compiler do that? Like for static
C?
const, yeah.
Oh, I just mostly what I said. You had a scope, which is basically a struct, and I did a lookup on the field name. But the parser told me that I was global scope variable. So at the time I have a load of it pointed I to a symbol table entry that said global scope. So when
of course,
in
C, of course, you say it's a const, so you already know it's a const.
No, it's independent. No, I'm doing value, nothing to do with const at all. This is unrelated to const. I'm doing value equivalence. I am loading a value against the global scope. I'll take the last store against the global scope, whether that's a const or not. It happens to be a const, great. But it doesn't have to be. I'm just taking whatever it is.
Okay, and then thanks for that. So the next thing I wanted to, maybe that's not a question, I just wanted to share what I've been doing with my language. If you go down to the next page, I think it's basically the idea of hybrid languages, right? So here, what you can do is you write Lua code, but you can embed C code inside it, and you can pass things in and out. So for example, here, if I just describe this, the first part is saying C declaration is like a keyword, and it takes a string argument, but you can define C structs inside
does it get type checked?
Yeah,
pass it like a string.
Does it get type checked by Lua, or does it just get passed on to the C compiler getting type checked?
So I've got a C parser.
Okay.
So the idea is that it will be parsed and checked and everything, right? Okay. But at the moment, my checking is rudimentary.
Yeah.
But anyway, so for example, pointers are not allowed, and certain things are not allowed. Fine. So you define your structs, and then as long as you've given the name to the struct, what you can do later on, as you can see in the next function, which is a Lua function, you say C new. So this creates what in Lua you have the ability to create what are called user data values, which are like heap allocated objects, which Lua doesn't care about, but they're garbage collected. So here we are saying, okay, create me a date object, and it will look up the type definition you provided before. And then in the next section, you've got some C code, and you're simply saying, this is an unsafe bit of C code. C code is in the string, but I'm passing it date DMY. So date is going to be a struct because it's a user data type. DMY are integer values, and so
Right. And then you
that's
wrote some
how
C
it
code.
works. And there's some C code that
Yeah.
you write. So you kind of you can have snippets of C code. You're not allowed certain things. You're not allowed, in my implementation, you're not allowed to make function calls. You're not allowed to do any go-tos or
Are you
returns.
parsing the C code?
Yeah.
Oh, and you're
You've got
actually
a-
building, you're not emitting the C code back out to a C compiler, you're actually emitting whatever you're emitting.
So the whole of this gets eventually emitted as C code, right?
Okay.
So whatever code you put in here will get pasted into the final code.
All right,
However,
will get pasted as C code.
Yes.
So you have arbitrary C code here.
You can, but however, I have a C code parser which will check everything.
Okay.
It checks things like that you can't have any function calls, you can't do returns.
So the subset that you allow of C that you allow.
Exactly.
Exactly. Okay.
So the idea is that my goal eventually is to have like a subset of C which is safe but fast. And eventually it gets all emitted as C code, and you can either JIT compile it or you can AOT compile it. You can just run it through GCC or Clang and produce a shared library, and you can run it.
Right.
Or you can I have a JIT compiler as well, so you can use the JIT compiler, which converts from C to machine code.
Right.
So anyway, the idea is
from the subset of C to machine code.
That's right.
Yeah, fine.
No, well, I'm using this project called Mir, which is a full-fledged JIT engine, and it has a C front end.
Yeah. Okay. Fine.
And so this is just a hybrid. I have not seen many attempts to do hybrid languages. Where you have two languages.
Yeah, they float around. Usually, people are embedding like SQL.
Yes, that's right. Sorry, I've got somebody on the door.
More of the approaches are like a DSL. You don't go to the second language, or you find a way to embed the second language in your language.
Right. So he's basically embedding a subset of C directly, and then he says he just pasted it to the C compiler later, which
yeah, but it's still C. It doesn't represent a DSL to C. It's
a foreign function interface.
Yeah,
but you can have C there between Lua and C. I think fine. I think it's reasonable. All right, I'm give you a bit to come back, but then I'm gonna bail unless somebody has any questions here. We're already at 12:30.
Yeah, so. It's kind of a long shot.
Yeah, right. I might try to do a sea of nodes discussion for next time and see how that goes.
That would be useful.
Pre-canned, a little cleaner to go through. Fine.
Okay.
Anyone else have anything they want to ask or throw out there? All right. Well, this was a long one, and boy, did it get deep quick. I at least had a lot of fun.
Yeah, it was fun.
All right, Yimdo, I'm gonna declare quits, and next week. It's 12:30 already. We're 2.5 hours in. It's pretty long.
Yeah.
All right. Till next time.
Bye.
Bye, everybody.
Bye.